Good evening, everyone. This is our first stream here, Security Plus study session. For tonight's topic, we're going to be covering cloud and virtualization security, uh, covering several different domains. I've already started this chapter. I'll give you a brief overview of what I've gone over. Just gives a brief description on exploring the cloud, what cloud computing is, touches on Amazon Web Services, AWS, Azure, Google, some of the benefits of the cloud, on-demand self-service computing, scalability, vertical scaling. Vertical scaling increases the capacity of existing servers. For example, you might change the number of CPU cores or the amount of memory assigned to a server. In the physical world, this means opening up a server and adding physical hardware. In the cloud, you can just click a few buttons and add memory or compute capacity. Horizontal scaling. Horizontal scaling adds more servers to a pool of clustered servers. If you run a website that supports 2,000 concurrent users with 2 servers, you might add a new server every time your typical usage increases another 1,000 servers. We touched on elasticity. Elasticity and scalability are closely related. Scalability is focused on rapidly increasing capacity. Elasticity says that capacity should expand and contract as needed. Change to optimize cost. If your website starts to experience a burst in activity, elasticity allows you to add servers automatically until that capacity is met, and then remove those servers when the capacity is no longer needed. Measured service. Everything you do in the cloud is measured by the provider. Providers track the number of seconds of processing time you consume, the right amount of storage you occupy, the number of log entries you generate, and many other measures. They use this information to be able to assess charges based on your usage. You pay for exactly what you use, no more, no less. Agility and flexibility. The speed to provision cloud resources and the ability to use them for short periods of time lends tremendous agility and flexibility to technology organizations. Developers and engineers who wish to try a new idea can rapidly spin up a test environment, evaluate the approach, and decide whether to move into production with minimal effort and cost. Cloud roles. Cloud service providers. Cloud service providers are the firms that offer cloud computing services to their customers. They may build their own data centers or work hand in hand with other cloud providers to deliver their service. But their defining characteristic is that they offer a cloud service for sale. Cloud consumers are the organizations and individuals who purchase cloud services from cloud service providers. They use these services to meet their own business requirements. Cloud partners, or cloud brokers, are organizations that offer ancillary products or services that support or integrate with the offerings of a cloud service provider. Cloud partners may offer training or consulting to help customers make use of a cloud service, provide software development and integration services, or perform any other service that facilitates the use of a cloud offering. Cloud auditors. Cloud auditors are independent organizations that provide third-party assessments of cloud services and operations. Depending on the scope of the audit engagement, they may provide a general assessment of a cloud environment or focus on security controls for narrow scope of operations. Cloud carriers serve as the intermediaries that provide the connectivity that allows the delivery of cloud services from providers to consumers. So cloud service providers, cloud consumers, cloud partners, cloud auditors, and cloud carriers. Note, the same organizations may take on multiple roles. For example, if an organization purchases cloud infrastructure components from a cloud service provider, they are a cloud consumer. If they use those infrastructure components to build a cloud software application that they offer to their own customers, then they are also a cloud service provider themselves. Cloud service models. We categorize the types of services offered by cloud service providers into several buckets based on the nature of the offering. The wide variety of services available in the cloud are often described as anything as a service, or the acronym XaaS, where X indicates the nature of the specific service. Although there are many different types of cloud service, we often describe them using three major service models: infrastructure as a service, IaaS; software as a service, SaaS; and platform as a service, PaaS. Infrastructure as a service. Infrastructure as a service, IaaS, offerings allow customers to purchase and interact with the basic building blocks of the technology infrastructure. These include computing, storage, and networks. Customers then have the flexibility to configure and manage those services in any way they like to meet their own business needs. The customer does not have to worry about the management of the underlying hardware, but they do have the ability to customize components to meet their needs. In the IaaS model, the cloud service provider is responsible for managing the physical facilities and the underlying hardware. The provider must also implement managing the physical facilities and underlying hardware. The provider must also implement security controls that prevent customers from eavesdropping on each other or interfering with each other's use of the infrastructure environment. Although there are dozens of IaaS providers in the marketplace today, the market is currently dominated by three major players: Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP. These three providers serve the vast majority of IaaS customers and offer a wide breadth of compute, storage, and networking products, as well as supplementary services that reside higher in the stack, such as security monitoring, content delivery networks, and application streaming. Software as a service. Software as a service offerings provide customers with access to a fully managed application running in the cloud. The provider is responsible for everything from the operation of the physical data centers to the performance management of the application itself. Although some of these tasks may be outsourced to other cloud service providers, in the SaaS model, the customer is only responsible for limited configuration of the application itself. The selection of what data they wish to use with what cloud solution, and the use of application provided access controls to limit access to that data. Okay. The SaaS model is widely used to deliver applications ranging from web-based email to enterprise resource planning, ERP, and customer relationship management, CRM suites. Customers enjoy continued access to cutting-edge software and typically pay for SaaS services using a subscription model. Users of the product normally access the application through a standard web browser and may even use a thin client device, such as the Google Chromebook. Platform as a Service. Platform as a Service, or PaaS, offerings fit into a middle ground between SaaS and IaaS solutions. In a PaaS offering, the service provider offers a platform where customers may run applications that they have developed themselves. The cloud service provider builds and manages the infrastructure and offers customers an execution environment, which may include code libraries, services, and tools that facilitate code execution. There's also Function as a Service, FaaS. Function as a Service platforms are an example of a PaaS computing. This approach allows customers to upload their own code functions to the provider, and then the provider will execute those functions on a scheduled basis in response to events and/or on demand. The AWS Lambda service is an example of a FaaS/PaaS offering. Lambda allows customers to write code in Python, Java, C Sharp, PowerShell, Node.js, Ruby, Go, and other programming languages. The Lambda function is a Python function designed to read the current temperature from an Internet of Things IoT temperature sensor. And then some of these have examples that I'm not going to be able to show. I mean, I might be able to take PDFs of it and put it up, but I'm mostly just going to be doing the reading, and then we'll go through and do the practice questions with the answers and explanations to them afterwards. So, where were we? Because FaaS environments do not expose customers to the actual server instances executing their code, they are often referred to as serverless computing environments. However, this is somewhat of a misnomer, since FaaS environments most certainly do have servers running the code, but they do so in a manner that is transparent to the FaaS customer. Managed services. Organizations may also choose to outsource some or all of the management of their technology infrastructure. Managed service providers, MSPs, are service organizations that provide information technology as a service to their customers. MSPs may handle an organization's IT needs completely, or they may offer focused services such as network design and implementation, application monitoring, or cloud cost management. MSPs are not MSPs are not necessarily cloud service providers themselves, although they may both although they may be both MSP and CSP, CSP being cloud service providers. They are typically capable of working across a customer's total environment, including both cloud and on-premises deployments. When MSPs offer security services, they are commonly referred to as Managed Security Service Providers, MSSPs. Services offered by MSSPs include security monitoring, vulnerability management, incident response, and firewall management. Uh, so moving on, we have cloud deployment models. Cloud deployment models describe how a cloud service is delivered to customers and whether the resources used to offer services to one customer are shared with other customers. Public cloud. When we think of the cloud, we commonly first think of public cloud offerings. Public cloud service providers deploy infrastructure and then make it accessible to any customers who wish to take advantage of it in a multi-tenant model. A single customer may be running workloads on servers spread throughout one or more data centers, and those servers may be running workloads for many different customers simultaneously. The public cloud supports all cloud service models. Public cloud providers may offer IaaS, PaaS, SaaS, and FaaS services to their customers. The key distinction in that those services do not run on infrastructure dedicated to a single customer, but rather on infrastructure that is available to the general public. AWS, Microsoft Azure, and GCP all use the public cloud model. Private cloud. The term private cloud is used to describe any cloud infrastructure that is provisioned for use by a single customer. This infrastructure may be built and managed by the organization that will be using the infrastructure, or it may be built and managed by a third party. The key distinction here is that only one customer uses the environment. For this reason, private cloud services tend to have excess unused capacity to support peak demand, and as a result are not as cost efficient as public cloud services. The intelligence community leverages a public uh, the intelligence community leverages a private public cloud. The US intelligence community, IC, has long been one of the largest, if not the largest, users of computing power in the world. In fact, many advances in computing began as projects in support of IC customers. As the private sector began a rapid migration to the public cloud, IC technologists took note but lamented that strict security requirement prevented them from using any multi-tenant environment for classified national security activities. IC technologists work with AWS to address this problem, and in 2014 launched the AWS Commercial Cloud Services (C2S) region that provides dedicated AWS services to IC customers. The region is operated by AWS but physically resides at a Central Intelligence Agency, the CIA facility, and is completely air-gapped from the internet, providing an incredibly high level of security. Moving on, the interesting thing about this approach is that it fits the definition of private cloud because AWS is operating the C2S region specifically for the IC, but it runs with the same tools and services available in the AWS public cloud, presumably at a much greater cost. In 2017, AWS announced the launch of the AWS Secret Region, an even broader effort designed to support any classified work across the US government. Microsoft also announced the availability of Azure Government Secret for the same purpose. The broad availability of those regions across government agencies makes the secret regions fit the definition of community cloud rather than private cloud. Moving on to community cloud. A community cloud service shares characteristics of both public and private models. Community cloud services do run in a multi-tenant environment, but the tenants are limited to members of a specifically designated community. Community membership is normally defined based on a shared mission, similar security and compliance requirements, or other commonalities. The HathiTrust Digital Library is an example of a community cloud in action. Academic research libraries join together to form a consortium that provides access to their collections of books. Students and faculty at Hathi Trust members' institutions may log into the Community Cloud service to access resources. Hybrid cloud. A hybrid cloud is a catch-all term used to describe cloud deployments that blend public, private, and/or community cloud services together. It is not simply purchasing both public and private cloud services and using them together. Hybrid clouds require the use of technology that unifies the different cloud offerings into a single, coherent platform. For example, a firm might operate their own private cloud for the majority of their workloads, and then leverage public cloud capacity when demand exceeds the capacity of their private cloud infrastructure. This approach is known as public cloud bursting. Another common reason for using hybrid cloud environments is a desire to move away from a centralized approach to computing that places a significant portion of an organization's infrastructure within a single environment toward a decentralized approach that reduces single points of failure by spreading technology components across multiple providers. AWS Outposts are examples of hybrid cloud computing. Customers of this service receive a rack of computing equipment that they install in their own data centers. The equipment in the rack is maintained by AWS but provisioned by the customer in the same manner that their AWS public cloud resources. This approach qualifies as hybrid cloud because customers can manage both their on-premises AWS outposts, private cloud deployment, and other public cloud AWS services through the same management platform. Moving on, a shared responsibility model. In some ways, cybersecurity work in a cloud-centric environment is quite similar to on-premises cybersecurity. No matter where our systems are hosted, we still need to think about the confidentiality, integrity, and availability of our data and implement strong access controls and other mechanisms that protect those primary objectives. However, cloud security operations also differ significantly from on-premises environments because cloud customers must divide responsibilities between one or more service providers and the customer's own cybersecurity teams. This type of operating environment is known as the shared responsibility model. Um, there's a figure that's shown here that shows the common division of responsibilities in infrastructure as a service, platform as a service, and software as a service environments, known as the responsibility matrix. Here's a picture of the AWS Outpost that offers hybrid cloud capability. Okay, here's the shared responsibility model for cloud computing. Um, I'll see if that's worth it, where I'll take a PDF of that and post that. Moving along, in some cases, the division of responsibility is straightforward. Cloud providers, by their nature, are always responsible for the security of both hardware and the physical data center environment. If the customer were handling either of those items, the solution would not fit the definition of cloud computing. The differences in responsibility come higher up in the stack and vary depending on the nature of the cloud service being used. In an infrastructure as a service environment, the customer takes over security responsibility for everything that isn't infrastructure: the operating system, applications, and data that they run in the infrastructure as a service environment. In a platform as a service solution, the vendor also takes on responsibility for the operating system, whereas the customer retains responsibility for the data being placed into the environment and configuring its security. Responsibility for the application layer is shared between the service provider and the customer, and the exact division of responsibilities shifts based on the nature of the service. For example, if the platform as a service platform provides runtime interpreters for customer code, the cloud provider is responsible for the security of those interpreters. In a software as a service environment, the provider takes on almost all security responsibility. The customer retains some shared control over the data, and they place in the software as a service environment and configuration of access controls around that data. But the software as a service provider is being paid to take on the burden of most operational tasks, including cybersecurity. Note: be sure to clearly document the division of responsibilities for cybersecurity tasks. This is particularly important in situations requiring compliance and external regulations. For example, organizations subject to the Payment Card Industry Data Security Standard (PCI DSS) should work with cloud providers to document the specific controls and responsibilities for meeting each one of the many PCI DSS requirements. Cloud providers are familiar with this process, and many host websites providing detailed mappings of their controls to common compliance regimes. If you prefer, I'm also streaming on YouTube. It's youtube.com at RAS7 period. There's a period at the end of RAS7, whichever platform you prefer to view the stream on. Um, anyway, moving right along. Cloud standards and guidelines. The cybersecurity community offers a variety of reference documents to help organizations come to a common understanding of the cloud and cloud security issues. The Cloud Reference Architecture, published by the National Institute for Standards and Technology, NIST, in their SP 500-292, offers a high-level taxonomy for cloud services. The cloud roles discussed earlier in this chapter are adapted from the NIST Cloud Reference Architecture. There's a figure here that shows a high-level view of NIST's vision for how the elements of the architecture fit together. So there's the cloud consumer, the cloud auditor, the cloud provider, the service orchestration, cloud service management, um, cloud broker, cloud carrier. Again, if you guys would like, I can put together PDFs of this material. Moving on. The Cloud Security Alliance, CSA, is an industry organization focused on developing and promoting best practices in cloud security. They developed the Cloud Controls Matrix, CCM, as a reference document designed to help organizations understand the appropriate use of cloud security controls and map those controls to various regulatory standards. The CCM is a lengthy Excel spreadsheet available for download. And then there's an available download link here. Cloud Controls Matrix Excerpt, uh, Cloud Security Alliance. Again, if you guys are interested, I can make a PDF out of that, but we're just going to keep moving here. Edge computing. The emergence of the Internet of Things, IoT, is dramatically changing the way that we provision and use computing. We see the most dramatic examples of the Internet of Things in our everyday lives, from connected and semi-autonomous vehicles to smart home devices that improve the way we live and travel. However, many of the applications of the Internet of Things occur out of sight in manufacturing plants, agricultural fields, and even in outer space. In situations where sensors are in remote locations with poor network connectivity, the traditional cloud model of shipping data back to the cloud for processing doesn't always work. Well, at least. Instead, it may make more sense to perform some processing close to the sensor to aggregate and minimize the data transferred back to the cloud. Edge computing approaches Edge computing approaches seek to address this issue by placing some processing power on the remote sensors, allowing them to pre-process data before shipping it back to the cloud. This model takes its name from the fact that computing is being pushed out to sensors that are located on the edge of the network. Let me just go over that one more time real quick. Edge computing approaches seek to address this issue by placing some processing power on the remote sensors, allowing them to pre-process data before shipping it back to the cloud. This model takes its name from the fact that computing is being pushed out to sensors that are located on the edge of the network. Then there's fog computing. Fog computing is a related concept that uses the IoT gateway devices that are located in close physical proximity to the sensors. The sensors themselves don't necessarily have processing power, but they send data to the local gateway that performs pre-processing before sending the results to the cloud. Okay, moving on to virtualization. Cloud computing providers, Cloud computing providers, as well as most other data center operators, make extensive use of virtualization technology to allow multiple guest systems to share the same underlying hardware. In a virtualized data center, the virtual host hardware runs a special operating system known as a hypervisor that mediates access to the underlying hardware resources. Virtual machines then run on top of this virtual infrastructure provided by the hypervisor, running standard operating systems, such as Windows and Linux variants. The virtual machines may not be aware that they are running in a virtualized environment because the hypervisor tricks them into thinking that they have normal access to the underlying hardware, when in reality, that hardware is shared with other systems. Hypervisors. The primary responsibility of the hypervisor is enforcing isolation between virtual machines. This means that the hypervisor must present each virtual machine with the illusion of a completely separate physical environment dedicated for use by that virtual machine. From an operational perspective, isolation ensures that virtual machines do not interfere with each other's operations. From a security perspective, it means that virtual machines are not able to access or alter information or resources assigned to another virtual machine. There are two primary types of hypervisors. Type 1 hypervisors, also known as bare metal hypervisors, operate directly on top of the underlying hardware. The hypervisor then supports guest operating systems for each virtual machine. This model most commonly used in data center virtualization because it is highly efficient. Okay, we have a little figure of a type 1 hypervisor there. We'll just go ahead and move on. Type 2 hypervisors. Type 2 hypervisors run as an application on top of an existing operating system, as shown in Figure 1010. In this approach, the operating system supports the hypervisor, and the hypervisor requests resources for each guest operating system from the host operating system. This model is commonly used to provide virtualization environments on personal computers for developers, technologists, and others who have the need to run their own virtual machines. It is less efficient than bare metal virtualization because the host operating system introduces a layer of inefficiency that consumes resources. Okay, virtualization, hypervisors, type 1 hypervisors, type 2 hypervisors. We'll go back and review all of this at the end of the chapter. The end of the chapter usually gives a good summary and things to know for the exam. And then it provides us with a practice exam as well. Okay, moving on. Cloud infrastructure components. IaaS computing environments provide organizations with access to a wide variety of computing resources, including compute capacity, storage, and networking. These resources are available in a flexible manner and typically may be used immediately upon request. And IaaS is infrastructure as a service. Cloud compute resources. Computing capacity is one of the primary needs of organizations moving to the cloud. As they seek to augment or replace the servers running on their own data centers, they look to the cloud for virtualized servers and other means of providing computing capacity. All of these technologies benefit from the cloud's dynamic resource allocation, allowing administrators to add and remove resources automatically or manually as needs change. Virtualization. Virtual machines are the basic building block of compute capacity in the cloud. Organizations may provision servers running most common operating systems with specific number of CPU cores, amount of RAM, and storage capacity that is necessary to meet business requirements. The cost of the cost of a server instance normally accrues based on an hourly rate, and that rate varies based on the compute, memory, and storage resources consumed by that server. Once you've provisioned a virtualized server, you may interact with it in the same manner as you would a server running in your own data center. So figure 1012 shows a SSH connection to a Linux infrastructure as a server instance. Provisioning a virtualized server in AWS. Okay. All right, let's move on there. Figure 1013 shows the use of a Microsoft remote desktop tool to connect to a Windows infrastructure as a service instance using the Remote Desktop Protocol, RDP, for graphical user interface. These tools allow administrators to interact normally with virtualized servers. Containerization. Containers provide application-level virtualization. Instead of creating complex virtual machines that require their own operating systems, containers package applications and allow them to be treated as units of virtualization that become portable across operating systems and hardware platforms. Organizations implementing containerization run containerization platforms such as Docker that provide standardized interfaces to operating system resources. This interface remains consistent regardless of the underlying operating system or hardware. and the consistency of the interface allows containers to shift between systems as needed. Containerization platforms share many of the same security considerations as virtualization platforms. They must enforce isolation between containers to prevent operational and security issues that might occur if an application running in one container is able to accidentally or intentionally interact with resources assigned to another container. Here we have a graph of provisioning a virtualized server in AWS. Choose an instance type. Take a look at that later, and again, if we need, we'll make that a PDF. Connecting to an AWS virtual server instance with SSH. Okay. All right, what is this? Connecting to an AWS virtual server instance with RDP. So that's that remote desktop protocol that I was talking about from Windows. Okay, just a little bit of reference. I don't think really any of these pictures should come into play on the exam, but I don't know for sure. I'll go ahead and review them later. I just want to do a one through the book, go back, highlight the key points, and then we'll go over key points, go over the summaries, and then go over the key details to know for the exam. And I have approximately 1,000 practice questions for us to run, which should be completely sufficient for the exam. Okay, moving along. Specific ways that we can secure containers recommended by NIST include using container-specific host operating systems, which are built with reduced features to reduce attack surfaces. Segmenting containers by risk profile and purpose, using container-specific vulnerability management security tools. Okay, exam note. Remember that containers provide application-level virtualization but must be protected like VMs. Enforced isolation between containers to prevent operational and security issues is recommended. Let's go over that one more time. Remember that containers provide application-level virtualization but must be protected like VMs. Enforced isolation between containers to prevent operational and security issues is recommended. Let me just see if we got anything going on in the chat. I see 18 people in here. Thanks to each one of you for being in here. Sorry, it's my first time running a space. I'm not totally sure what I'm doing. Okay, sorry about that. I was just trying to see if I could see the chat. Broadcast details, flip camera. All right. I don't see anything in the chat. If you guys need to, just go ahead and leave a comment down below. If you have any specific questions or anything in specific that you want reviewed, and we can go ahead and review that. Okay, let's move along. Cloud storage resources. Infrastructure providers also offer their customers storage resources. Both storage that is coupled with their computing offerings and independent storage offerings for use in building other cloud architectures. These storage offerings come in two major categories. Block storage. Block storage allocates large volumes of storage for use by virtual server instances. These volumes are then formatted as virtual disks by the operating system on those server instances and used as they would be a physical drive. AWS offers block storage through their Elastic Block Storage (EBS) service. Figure 1014 shows a series of EBS volumes allocated for use with virtual servers. Just taking a quick glance at that. Okay, a little bit of reference, have some idea of what's going on there. Okay, object storage. Object storage provides customers with the ability to place files in buckets and treat each file as an independent entity that may be accessed over the web or through the provider's API. Object storage hides the storage details from the end user, who does not know or care about the underlying disks. The AWS Simple Storage Service, S3, is an example of an object storage. Figure 1015 shows an example of a S3 storage bucket. Let's take a quick look at that. Okay. Note: block and object storage incur costs in different ways. Block storage is pre-allocated by the cloud provider, and you pay for the capacity that you allocated, regardless of whether you actually store data on. Let's start that from the top. Block and object storage incur costs in different ways. Block storage is pre-allocated by the cloud provider, and you pay for the capacity that you allocated, regardless of whether you actually store data on that volume. If you allocate a 1 terabyte drive, you will pay for 1 terabyte of storage, even if you are only storing only 500 gigabytes of data on the drive. Object storage is not pre-allocated, and you pay for the storage that you use. Block storage is also significantly more expensive than object storage. As of this writing, block storage charges at major cloud providers were 3 to 10 times higher than object storage charges. So we got block storage, which you pay for an allocated amount, and then we have object storage, which is not pre-allocated, and you pay for the storage that you use. Okay, moving on. As you work with cloud storage, be certain that you keep 3 key security considerations top of mind. Set permissions properly. Make sure that you pay careful attention to the access policies you place on storage. This is especially true for object storage, where a few wayward clicks can inadvertently publish a sensitive file on the web. So set permissions properly. Consider high availability and durability options. Cloud providers hide and implementation details from users, but that doesn't mean they are immune from hardware failures. Use the provider's replication capabilities or implement your own to accommodate availability and integrity requirements. Let's consider high availability and durability options. Third, use encryption to protect sensitive data. You may either apply your own encryption to individual files stored in the cloud or use the full disk encryption options offered by the provider. Figure 1016 shows the process of enabling full disk encryption on an AWS EBS volume. Okay. Encryption, encrypt this volume. Okay. Again, just please feel free to leave me some kind of comment if you're interested in some of these figures that they're providing. If you want like a compilation of those, I'll be happy to make those. Let's go ahead and keep moving. Flowing around this chapter pretty good here. All right. Cloud networking. Cloud networking follows the same virtualization model as other cloud infrastructure resources. Cloud consumers are provided access to networking resources to connect their other infrastructure components and are able to provision bandwidth as needed to meet their needs. Cloud networking supports the software-defined networking (SDN) movement by allowing engineers to interact with and modify cloud resources through their APIs. Similarly, they provide cybersecurity professionals with software-defined visibility (SDV) that offers insight into the traffic on their virtual networks. Uh, if you guys don't mind, let's run over that one more time. Cloud networking supports the software-defined networking (SDN) movement by allowing engineers to interact with and modify cloud resources through their APIs. Similarly, they provide cybersecurity professionals with software-defined visibility (SDV) that offers insight into the traffic on their virtual networks. Okay. Security groups. Security professionals use firewalls on their physical networks to limit the types of network traffic that are allowed to enter the organization's secured perimeter. Cloud service providers implement firewalls as well, but they do not provide customers with direct access to those firewalls, because doing so would violate the isolation principle by potentially allowing one customer to make changes to the firewall that would impact other customers. Instead, cloud service providers meet the need for firewalls through the use of security groups that define permissible network traffic. These security groups consist of a set of rules for network traffic that are substantially the same as a firewall rule set. Figure 1017 shows an example of a security group. Security group restricting access to a cloud server, inbound rules, type, protocol, port range, source, description. Okay, moving on. Note, security groups function at the network layer of the OSI model, similar to a traditional firewall. Cloud service providers also offer web application firewall capabilities that operate at higher levels of the OSI model. Uh, Security groups are normally considered a feature of a provider's virtual servers and, as such, do not incur additional costs. Security groups are normally considered a feature of a provider's virtual servers and, as such, do not incur additional costs. Okay. Virtual Private Cloud, VPC. Segmentation is one of the core concepts of network security. Segmentation allows network engineers to place systems of differing security levels and functions on different network subnets. Similarly grouped systems are able to communicate with each other while remaining isolated from systems on other network segments. On a physical network, networking and security professionals use virtual LAN, otherwise known as VLANs, technology to achieve segmentation. In a cloud environment, virtual private clouds, VPCs, serve the same purpose. Using VPCs, virtual private clouds, teams can group systems into subnets and designate those subnets as public or private, depending on whether access to them is permitted from the internet. Cloud providers also offer VPC endpoints that allow the connection of VPCs to each other using the cloud provider's secure network backbone. Cloud transit gateways extend this model even further, allowing the direct interconnection of cloud VPCs with on-premises VLANs for hybrid cloud operations. Really getting into it here, huh? Figure 1018 shows the process of creating a VPC and specifying whether the VPC should have public and/or private subnets. Figure 1018, creating a virtual private cloud. Select the VPC configuration, VPC with single public subnet, VPC with public and private subnets, VPC with public and private subnets and hardware VPN access, VPC with a private subnet only, and hardware VPN access. Okay. Just a little reference model there. Let's keep it moving. Again, sorry folks, this is my first time live streaming anything. I'm simultaneously streaming here on Twitter. I see 20 people on here. I don't think I have anybody watching me on YouTube, but streaming there, I see on YouTube I can also do a screen share. So I might even potentially be able to put some of this material on there. I'll try to improve on the production of things as we go on. I just wanted to kind of see if there would be any audience or if I would just be basically reading to myself. But since there's people tuned in, let's go ahead and proceed. I just wanted to thank each and every one of you for stopping by. Hope you get some value out of this. Okay, here we go. DevOps and cloud automation. Traditional approaches to organizing and running technology teams focused on building silos of expertise centered on technology roles. In particular, software development and technology operations were often viewed as quite disconnected. Developers worked on creating the software applications that the business desired and had their own process for specifying requirements, designing interfaces, writing code, testing applications, and maintaining the code base. When they completed testing of a new version of an application, they then handed it off to the technology operations team, who managed the servers and other infrastructure supporting the application. Separating the development and operations worlds provides technologists with a comfortable working environment where they have their tasks clearly defined and are surrounded by a community of their peers. It also, however, brings significant disadvantages, including the following. Isolating operations teams from the development process inhibits their understanding of business requirements. Isolating developers from operational considerations leads to designs that are wasteful in terms of processor, memory, and network consumption. Requiring clear hands-off from development to operations reduces agility and flexibility by requiring a lengthy transition phase. Increasing the overhead associated with transitions encourages combining many small fixes and enhancements into one major release, increasing the time to requirement satisfaction. Okay, moving along. Recognizing the inherent disadvantages of separating development and operational teams, many organizations now embrace a DevOps approach to technology management. This approach brings together development and operation teams in a unified process where they work together in an agile approach to software development. The software testing and release process becomes highly automated and collaborative, enabling organizations to move from lengthy release management processes to a world where they might release dozens of updates on a daily basis. Infrastructure as Code, IAC, is one of the key enabling technologies behind the DevOps movement and is a crucial advantage of cloud computing services integration. IAC is the process of automating the provisioning, management, and deprovisioning of infrastructure services through scripted code rather than human intervention. IAC is one of the key features of all major IaaS environments, including AWS, Azure, and GCP. Again, IaaS is infrastructure as a service. IAC takes many forms and may be either a feature offered by a cloud service provider or a functionality enabled by a third-party cloud management platform. In most cases, the same actions available to operations teams through the cloud provider's web interface are also available for implementation in code. AWS offers a service called CloudFormation that allows developers to specify their infrastructure equipment, their infrastructure requirements in several formats, including JavaScript, Object Notation, JSON, and YAML, 8 markup language. Figure 1019 shows an example of the JSON specification for the EC2 instance. Creating an EC2 instance with CloudFormation JSON. It looks like some code here. Okay, have to reference that later. Let's keep reading. Let's keep moving along. Infrastructure as code approaches depend on the use of application programming interfaces, APIs. APIs are application programming interfaces offered by cloud providers. Developers can use cloud provider APIs to programmatically Let's start that from the top. I'm not sure what happened. I swear I can read. Infrastructure as code approaches depend on the use of application programming interfaces, APIs, offered by cloud providers. Developers can use cloud provider APIs to programmatically provision, configure, modify, and deprovision cloud resources. API integration is particularly helpful in cloud environments that embrace microservices, cloud service offerings that provide very granular functions to other services, often through a function as a service model. These microservices are designed to communicate with each other in response to events that take place in the environment. All right. Covering a lot of stuff, at least so far. We'll try to do a good review of everything at the end. Let's just keep pushing. Cloud security issues. The cloud brings tremendous operational and financial advantages to organizations, but those advantages also come with new security issues that arise in cloud environments. Availability. Availability issues exist in cloud environments, just as they do on on-premises settings. One of the major advantages of the cloud is that cloud providers may operate in many different geographic regions, and they often provide simple mechanisms for backing up data across those regions and/or operating in a high availability mode across diverse zones. For example, a company operating a web server cluster in the cloud may choose to place servers on each major continent to serve customers in those regions and also to provide geographic diversity in the event of a large-scale issue in a particular geographic region. Exam note. These exam notes are usually very important and things that we want to focus on. Exam note. It is very important to understand that high availability is not always guaranteed with base level cloud services. You often need to purchase and/or configure high availability services in order to maximize your uptime. Okay. Moving along. Data sovereignty. As you just read, the distributed nature of cloud computing involves the use of geographically distant facilities to achieve high availability and to place content in close proximity to users. This may mean that a customer's data is stored and processed in data centers across many different countries, either with or without explicit notification. Unless customers understand how their data is stored, this could introduce legal concerns. Data sovereignty is a principle that states that data is subject to the legal restrictions of any jurisdiction where it is collected, stored, or processed. Under this principle, a customer might wind up subject to the legal requirements of a jurisdiction where they have no involvement other than the fact that one of their cloud providers operates a data center within that jurisdiction. Security professionals responsible for managing cloud services should be certain that they understand how their data is stored, processed, and transmitted across jurisdictions. They may also choose to encrypt data using keys that remain outside the provider's control to ensure that they maintain sole control over their data. Some cloud providers offer explicit control over the use of resources in specific regions. For example, Figure 1020 shows the controls used by Zoom users to block the use of data centers located in China or Hong Kong. Limiting the data center regions used for a Zoom meeting. Enable data centers, China and Hong Kong. Okay. Just basically a settings screenshot for Zoom on how to limit the data center regions used for that. Okay, let's keep moving. See what we got. Anything? 24 people. Shout out to y'all. 24. That's what's up. Still 0 on YouTube, I see. That's cool. That's cool. All right. Virtualization security. Virtual machine VM escape vulnerabilities are the most serious issue that can exist in a virtualized environment, particularly when a virtual host runs systems of differing security levels. In an escape attack, the attacker has access to a single virtual host and then manages to leverage that access to intrude upon the resources assigned to a different virtual machine. The hypervisor is supposed to prevent this type of access by restricting a virtual machine's access to only those resources assigned to that machine. Escape attacks allow a process running on a virtual machine to escape those hypervisor restrictions. Virtual machine sprawl occurs when infrastructure as a service users create virtual service instances and then forget about them or abandon them, leaving them to accrue costs and accumulate security issues over time. Organizations should maintain instance awareness to avoid VM sprawl issues. VM sprawl issues, virtual machine sprawl issues. Okay. Resource reuse occurs when cloud providers take hardware resources that were originally assigned to one customer and reassign them to another customer. If the data was not properly removed from that hardware, the new customer may inadvertently gain access to data belonging to another customer. Okay, we got another exam note that's coming up here. Exam Objective 2.3 calls out virtual machine, VM escape, and resource reuse. Be sure you are familiar with and can explain these virtualization vulnerabilities. Okay, so let's review that real quick. Virtual machine escape and resource reuse. Virtual machine escape. Okay, let's read that again. Virtual machine escape vulnerabilities are the most serious issue that can exist in a virtualized environment, particularly when a virtual host runs systems of differing security levels. In an escape attack, the attacker has access to a single virtual host and then manages to leverage that access to intrude upon the resources assigned to a different virtual machine. The hypervisor is supposed to prevent this type of access by restricting a virtual machine's access to only one of those resources assigned to that machine. Escape attacks allow a process running on the virtual machine to escape those hypervisor restrictions. And then resource reuse occurs when cloud providers take hardware resources that were originally assigned to one customer and reassign them to another customer. If the data was not properly removed from that hardware, the new customer may inadvertently gain access to data belonging to another customer. Okay. So be sure you are familiar with and can explain these virtualization vulnerabilities. Virtual machine escape and resource reuse. Just went over those. Okay. Keeping it moving. Let me just grab the Zoom real quick. All right. Where were we? Okay. Application security. Cloud applications suffer from many of the same security concerns as application security. Cloud applications suffer from many of the same security concerns as any other application. These software security issues were covered in Chapter 6, Application Security. Cloud applications depend heavily on the use of APIs to provide service integration and interoperability. In addition to implementing the secure coding practices discussed in Chapter 6, security analysts responsible for API-based applications should implement API inspection technology that scrutinizes API requests for security issues. These capabilities are found in web application firewall solutions. Secure web gateways, SWGs, also provide a layer of application security for cloud-dependent organizations. Secure web gateways monitor web requests made by internal users and evaluate them against the organization's security policy, blocking requests that run afoul of these requirements. Secure web gateways are commonly used to block access to potentially malicious content, but may also be used to enforce content filtering restrictions. All right. a lot to take in here. We'll definitely be reviewing the different chapters here, except I'll try to go through and highlight key points so that we're not just reading the full chapters unless you guys find that of value and you want to be reading the full chapters. But I'll try to have it curtailed a little bit to just only highlight key points that we should be going over. Okay. All right. Moving right along. Governance and auditing of third-party vendors. Technology governance efforts guide the work of IT organizations and ensure that they are consistent with organizational strategy and policy. These efforts also should guide an establishment and These efforts also should guide the establishment and maintenance of cloud third-party vendor relationships. Cloud governance efforts assist with the following: vetting vendors before considering for cloud partnerships, managing vendor relationships and monitoring for early warning signs of vendor stability issues, overseeing an organization's portfolio of cloud activities. Auditability is an important component of cloud governance. Cloud computing contracts should include language guaranteeing the right of the customer to audit cloud service providers. They may choose to perform these audits themselves or engage a third party to perform an independent audit. The use of auditing is essential to providing customers with the assurance that the provider is operating in a secure manner and meeting its contractual data protection obligations. Next section, hardening cloud infrastructure. Cloud providers and third-party organizations offer a variety of solutions that help organizations achieve their security objectives in the cloud. Organizations may choose to adopt cloud-native controls offered by their cloud service provider, third-party solutions, or a combination of the two. The purpose of all of these controls is hardening the cloud infrastructure against attack. Controls offered by cloud service providers have the advantage of direct integration with the provider's offerings, often making them cost-effective and user-friendly. Third-party solutions are often more costly, but they bring the advantage of integrating with a variety of cloud providers, facilitating the management of multi-cloud environments. Cloud access security brokers. Most organizations use a variety of cloud service providers for different purposes. It's not unusual to find that a large organization purchases cloud services from dozens or even hundreds of different providers. This is especially true when organizations use highly specialized software as a service products. Managing security policies consistently across these services poses a major challenge for cybersecurity analysts. Cloud access security brokers, CASBs, cloud access security brokers, are software tools that serve as intermediaries between cloud service users and cloud service providers. This positioning allows them to monitor user activity and enforce policy and requirements. CASBs operate using two different approaches. Inline CASB solutions physically or logically reside in the connection path between the user and the service. They may do this through a hardware appliance or an endpoint agent that routes requests through the CASB. This approach requires configuration of the network and/or endpoint devices. It provides the advantage of seeing requests before they are sent to the cloud service, allowing the CASB to block requests that violate policy. And then we have API-based CASB solutions. API-based CASB solutions do not interact directly with the user, but rather interact directly with the cloud provider through the provider's API. This approach provides direct access to the cloud service and does not require any user device configuration. However, it also does not allow the CASB to block requests that violate policy. API-based CASBs are limited to monitoring user activity and reporting on or correcting policy violations after the fact. Okay. Saw some hearts coming in. Thank you for that. Appreciate you guys. All right. Let's see where we're at. Did we get that? The cloud access security brokers, they break down into inline CASB solutions and API-based CASB solutions. Okay. We can go over any of this that you guys want later on. Go through that. Moving right along, we have resource policies. Cloud providers offer resource policies that customers may use to limit the actions that users of their accounts may take. Implementing resource policies is a good security practice to limit the damage caused by an accidental command, a compromised account, or a malicious insider. Here is an example of a service control policy written in JSON that restricts access to cloud resources. I'm not sure if you guys want me to exactly go through it, but it's just basically a JSON that offers a statement, condition. Again, I'll try to set up a PDF for some of these resources if you want, or if you follow me onto YouTube, I can just do a screen share there. I'm not sure exactly how to do a screen share here through Twitter. If anybody wants to help me out with that, I'll be happy to do that. Or I can just start streaming through the computer on X. All right, let's keep going. More of a JSON. It just basically gives you the entire script here. Restricts access to cloud resources. Okay. This policy prohibits affected users from using any resources outside of the US East and EU West regions and prohibits them from using some services such as identity and access management in any region. It also limits users to only launching smaller server instances in an effort to control costs. Okay. Secrets management. Hardware security modules, HSMs, are special purpose computing devices that manage encryption keys and also perform cryptographic operations in a highly efficient manner. This is hardware security modules, HSMs, are special purpose computing devices that manage encryption keys and also perform cryptographic operations in a highly efficient manner. HSMs are expensive to purchase and operate, but they provide an extremely high level of security when configured properly. One of their core benefits is that they can create and manage encryption keys without exposing them to a single human being, dramatically reducing the likelihood that they will be compromised. Those are hardware security modules, HSMs. Cloud service providers often use HSMs internally for the management of their own encryption keys and also offer HSM services to their customers as a secure method for managing customer keys without exposing them to the provider. All right, thank you so much for sticking through this far. We made it to the summary. I'm going to go ahead and briefly review the summary, and then we're going to go over the exam essentials, which I feel like highlights the key components of the chapter that we want to know for the exam. And then I have 20 review questions for us afterwards that we'll go over. All right, summary. Cloud computing changes the cybersecurity landscape. Although cybersecurity professionals still must implement controls that protect the confidentiality, integrity, and availability of information and systems, they do so in an environment that requires the cooperation of cloud service providers. Under the shared responsibility model of cloud security, cloud customers and providers must come to a common understanding of who will be responsible for meeting each security control requirement. Organizations adopting cloud security controls may choose to implement cloud-native security controls offered by their providers, third-party controls that work across a variety of environments, or a mixture of the two. They may implement cloud access security brokers, CASBs, that allow the consistent enforcement of security policies across diverse cloud platforms. Organizations should also understand the vulnerabilities that appear in cloud environments. These include virtualization issues such as virtual machine escape and resource reuse. Using cloud services located in different jurisdictions may also introduce data sovereignty concerns. Okay, sliding down to exam essentials. I think this is the most important part of the chapter here, so we'll really focus on this. Exam essentials. Explain the three major cloud service models. In the anything as a service XaaS approach to computing, there are three major cloud service models: infrastructure as a service, IaaS, offerings allow customers to purchase and interact with the basic building blocks of a technology infrastructure. Then we have software as a service, SaaS. Offerings provide customers with access to a fully managed application running in the cloud. Platform as a service, PaaS. Offerings provide a platform where customers may run applications that they have developed themselves. Okay, so knowing the three major cloud service models. Infrastructure as a service, software as a service, and platform as a service. Describe the four major cloud deployment models. So here we have public cloud service provides describe the four major cloud deployment models. Public cloud service providers deploy infrastructure and then make it accessible to any customers who wish to take advantage in a multi-tenant model. The term private cloud is used to describe any cloud infrastructure that is provisioned for use by a single customer. A community cloud service shares characteristics of both public and private models. Community cloud services do run in a multi-tenant environment, but the tenants are limited to members of a specifically designed Designed community. Hybrid cloud is a catch-all term used to describe cloud deployments that blend public, private, and/or community cloud services together. So describing the four major cloud deployment models: public cloud, private cloud, community cloud, and hybrid cloud. Understand the shared responsibility model of cloud security. Under the shared responsibility model of cloud security, cloud customers must divide responsibilities between one or more service providers and the customer's own cybersecurity teams. In an infrastructure as a service environment, the cloud provider takes on most responsibility, providing security for everything below the operating system layer. In a platform as a service, the cloud provider takes over added responsibility for the security of the operating system itself. In a software as a service, the cloud provider is responsible for the security of the entire environment, except for the configuration and access controls within the application and the choice of data to store in the service. Okay, so understanding the shared responsibility model. Um, what does IaaS environment do security wise? What does PaaS do security wise? And what does software as a service do security wise? Okay, and lastly, we have implement appropriate security controls in a cloud environment. Cloud customers should understand how to use the controls offered by providers and third parties to achieve their security objectives. This includes maintaining resource policies and designing resilient cloud implementations that achieve high availability across multiple zones. From a storage perspective, cloud customers should consider permissions, encryption, replication, and high availability. From a network perspective, cloud customers should consider the design of a virtual network with public and private subnets to achieve appropriate segmentation. From a compute perspective, customers should design security groups that appropriately restrict network traffic to instances and maintain the security of those instances. Okay, so we made it through that chapter. That was chapter 10. Um, Here we got 20 review questions. Do you guys want to do the review questions together? Do you want me to do a PDF of them on my iPad and take notes on it and upload the videos? I'm not sure what you guys prefer, but let's just go ahead and read through the questions at least and go through all the options and see what we can come up with. Chapter 10. Get ready. I'll actually go ahead and do the test and see how I score. Okay, review questions. Number 1. Kevin discovered that his web server was being overwhelmed by traffic, causing a CPU bottleneck. Using the interface offered by his cloud service provider, he added another CPU to the server. What term best describes Kevin's action? A. Elasticity. B. Horizontal scaling. C. Vertical scaling. Or D. High availability. I'll go through and read all the questions. We'll answer them and then we'll come back and compare the answers and then look at the answer guide, if that sounds like a plan. So that was number one. Uh, Number two, Fran's organization uses a Type 1 hypervisor to implement an infrastructure as a service offering that it sells to customers. Which one of the following security controls is least applicable to this environment? A. Customers must maintain security patches on guest operating systems. B. The provider must maintain security patches on the hypervisor. C. The provider must maintain security patches on the host operating system. D. Customers must manage security groups to mediate network access to guest operating systems. 3. In what cloud security model does the cloud service provider bear the most responsibility for implementing security controls? A. Infrastructure as a service. B. FaaS. C. Platform as a service. Or D. Software as a service. 4. Greg would like to find a reference document that describes how to map cloud security controls to different regulatory standards. What document would best assist with this task? The CSA CCM, option A, CSA CCM, option B, NIST SP 500 292, C, ISO 27001, D, PCI DSS. 5. Wanda is responsible for a series of seismic sensors placed okay. 5. Wanda is responsible for a series of seismic sensors placed at remote locations. These sensors have low bandwidth connections, and she would like to place the computing power on the sensors to allow them to pre-process data before it is sent back to the cloud. What term best describes this approach? Edge computing, client-server computing, or A, edge computing, B, client-server computing, C, fog computing, D, thin client computing. 6. Which one of the following statements about cloud computing is incorrect? A. Cloud computing offers ubiquitous, convenient access. B. Cloud computing customers store data on hardware that is shared with other customers. C. Cloud computing customers provision resources to the service provider's sales team. D. Cloud computing resources are accessed over a network. Okay. 7. Helen designed a new payroll system that she offers to her customers. She hosts the payroll system in AWS and her customers access it through the web. What tier of cloud computing best describes Helen's service? A. PAS, PaaS. B. SaaS. C. FaaS. D. IaaS. 8. Which cloud computing deployment model requires the use of unifying technology platform to tie together components from different providers? Let's read that one more time. 8. Which cloud computing deployment model requires the use of unifying technology platform to tie together components from different providers? A. Public cloud. B. Private cloud. C. Community cloud. D. Hybrid cloud. 9. Which one of the following would not commonly be available in an IaaS service offering? CRRM, A. CRM, B. Storage, C. Networking, D. Computing. 10. Which one of the following is not an example of an infrastructure as code? A. Defining infrastructure in JSON. B. Writing code to interact with a cloud provider's API. C. A cloud provider's web interface to provision resources. D. Defining infrastructure in YAML. 11. Brian is selecting a CASB for his organization, and he would like to use an approach that interacts with the cloud provider directly. Which CASB approach is the most appropriate for his needs? Inline CASB, outsider CASB, comprehensive CASB, API-based CASB. So again, the options for number 11 were A, inline CASB, B, outsider CASB, C, comprehensive CASB, or D, API-based CASB. 12. In which of the following cloud categories are customers typically charged based on the number of virtual server instances dedicated to their use? A. IaaS only. B. SaaS only. C. IaaS and PaaS. Or D. IaaS, SaaS, and PaaS. So that would be infrastructure as a service, software as a service, or platform as a service. Okay. 13. Brian would like to limit the ability of users inside his organization to provision expensive cloud server instances without permission. What type of control would best help him achieve this goal? Brian would like to limit the ability of users inside his organization to provision expensive cloud server instances without permission. What type of control would help him achieve this goal? A. Resource policy. B. Security group. C. Multi-factor authentication. D. Secure web gateway. 14. Ursula would like to link the networks in her own on-premises data center with cloud VPCs in a secure manner. What technology would help her best achieve this goal? A. Transit gateway. B. HSM. C. VPC endpoint. D. SWG. 15. What component of a virtualization platform is primarily responsible for preventing VM escape attacks? A. Administrator. B. Guest operating system. C. Host operating system. D. Hypervisor. 16. Ryan is selecting a new security control. All right, 16. Ryan is selecting a new security control to meet his organization's objectives. He would like to use it in their multi-cloud environment and would like to minimize the administrative work required from his fellow technologists. What approach would best meet his needs? A. Third-party control. B. Internally developed control. C. Cloud-native control. D. Any of the above. 17. Kira would like to implement a security control that can implement access restrictions across all of the software as a solution SaaS solutions used by her organization. What control would best meet her needs? A. Security group. B. Resource policy. C. CASB. D. SWG. 18. Howard is assessing the legal risks to his organization based on its handling of PII, that's privately identifiable information. The organization is based in the United States, handles the data of customers located in Europe, and stores information in Japanese data centers. What law would be most important to Howard during his assessment? A. Japanese law. B. European Union law. C. US law. D. All should have equal weight. 19. Brenda's company provides a managed incident response service to its customers. What term best describes this type of service offering? A. MSP. B. Platform as a service. C. Software as a service. D. MSSP. Managed Service Security Provider. 20. Tony purchases virtual machines from Microsoft Azure exclusively for his use by his organization. What model of cloud computing is this? A. Public cloud. B. Private cloud. C. Hybrid cloud. D. Community cloud. So we just went over all the questions. Do you guys want to go over them here in the live stream, or do you want me to post them individually on my timeline and then give the answers out that way? I can do either one, whichever is the most preferred by you guys. We can either do that and do the questions, or save those and let's see how many pages is. It's already 2:20 in the morning here. Our next section is endpoint security. We'll be discussing domain 1, general security concepts. Domain 2, threats, vulnerabilities, and mitigations. Domain 3, security architecture. Domain 4, security operations. And yeah, let me just get an idea of how many pages we're looking at. 340. So this is about another 30 pages or so, which I think is going to run me a little bit too late into the evening. So I think we'll leave it for right there. I see there's 24 people that were logged in. Thank you all for watching. I'll try to work on and prepare a little bit better for the live streams. This was my first time doing this. Was multi-streaming here on Twitter and on YouTube. If you guys, there's 24 of you in here. If you wouldn't mind, if you could go to youtube.com @RAS7 period. There's a period, a dot at the end of RAS7, and subscribe to my channel there. If I can get 50 subscribers on my YouTube there, I can start streaming on my mobile device, where I could be streaming questions and study material there as well. Yeah, I think I want to go back through this chapter, highlight specific points. There's a lot of terminology that I'm seeing here in the review questions. that I'm not totally familiar with and don't have memorized. I'm basically just trying to do a quick run through of this book here. Uh, if you see it here, I'm trying to do a run through of this, and then I'm going to supplement it with Professor Messer's videos, so I kind of have a little bit of a better understanding of what's going on there. But I think I'm going to call it for tonight. Um, Thank you to each and every one of you that tuned in. I hope you got some kind of value from this. Again, this was my first time streaming, and I hope to improve in the future. Thank you so much for tuning in tonight, and I hope each and every one of you have a great night.